All right, so here is bonding part 2. We're going to pick up with Lewis dot structures. We can draw a Lewis dot structure for an atom or for a compound. The rules are a little bit different if it's ionic or covalent. Essentially, a Lewis dot structure, or just a Lewis structure, is a model we use to visualize how the atoms are bonding together. It allows us to predict how many, if it's covalent bonds, how many covalent bonds will form. It allows us to predict then the shape of a molecule, which then allows us to predict things like polarity and intermolecular forces. So if we're drawing just a Lewis dot structure for an atom, we're going to have the symbol for the atom. So I'm going to draw a dot structure for nitrogen. And then we have to draw dots representing the valence electrons, right? And nitrogen has 5 valence electrons. So remember that we put 1 dot on each side, and then we start to double up. So nitrogen's 5 valence electrons would be shown like that. If I wanted to show an ionic compound, let's say for calcium chloride, being ionic, there's no covalent bonds. In a covalent bond, we're going to see here that we use a line to represent the sharing of electrons, but electrons were transferred here. And calcium has 2 valence electrons that were transferred over to chlorine. Chlorine has 7. Calcium is going to give up its 2 valence electrons. One goes to one chlorine, one goes to another. These now form ions. Remember that the Lewis structure for an ion has brackets around the symbol and then a charge. And we show how many electrons are in that valence shell now, whether it's after the metal lost, there will be none, or after the nonmetal gained, in which case they will have 8. In a covalent compound, let's take water as a simple example. The oxygen and the hydrogen are sharing electrons. For very simple covalent substances, we used the Honk rule to predict how many bonds they were going to make. Of course, it all goes back to how many valence electrons they have. Oxygen will make 2 bonds, hydrogen will make 1, and then we fill in the rest as lone pairs. Remember, oxygen has 6 valence electrons, so as just an oxygen atom, that's what it would look like. Each hydrogen has 1, so that's how the water bonds, but we represent the bonding pair of electrons as a line typically, and the lone pair is just a dot, or a pair of dots, I should say, of electrons. So that's a quick review of Lewis dot structures. We then looked at hybridization theory, which helped us to explain some other properties, shapes, and the like of some more complex molecules. And the idea here was that while bonding, the valence orbitals that contain the valence electrons sort of go into this atomic blender, if you will, and they hybridize and come out as hybrid orbitals. And the main molecule, I was looking for it here, CH4, that we used to explain hybridization was methane. And the reason why we used it was we looked at carbon's electron configuration, its orbital diagram. And we notice that there's 2 electrons in the 2s sublevel and 2 in the 2p. So even though there's 4 electrons in the outer shell, 2 of them are on a different sublevel than the other 2, which means they're of different energy, which means that these bonds should be different. And the way that this is drawn, these 2 electrons are paired, where these 2 electrons are unpaired. So it looks like carbon should only bond 2 times, but we know it bonds 4 times. So we use hybridization as a sort of hand-waving technique to really explain why we see the bonding that we do. And you should be familiar with the different types of hybridization that we went over in class. Methane specifically, we have 1s and 3 separate p orbitals that blend together to form 4 new, what we call sp3 orbitals. Those 4 sp3 orbitals have equal energy with 1 electron in each orbital, which then allows carbon to bond 4 times and allow those 4 bonds to be equivalent. But we saw that hybridization exists in other substances too. It's not just things that bond 4 times. So we have sp hybridization, in which the central atom has 2 regions of electron density, or 2 electron domains. sp2, where the central atom has 3 regions of electron density, or 3 electron domains. Of course, sp3 has 4 electron domains around the central atom. sp3d has 5 domains, and sp3d2 has 6. VSEPR, or technically it's valence shell electron pair repulsion, but we pronounce it VSEPR. This theory is used to help us predict what the shape around a central atom will be. And that allows us to predict the shape of an overall molecule, or the multiple shapes that exist in larger molecules. So what we're seeing here is this would be a formula for NH3. Here's the Lewis structure for NH3 based on the rules we just talked about. And then VSEPR theory says, okay, let's figure out what is the 3-dimensional shape around that nitrogen. Well, there's 4 electron domains, 3 bonded domains, and 1 lone pair. Those 4 domains are going to arrange themselves in a tetrahedron, but the shape here is not tetrahedral because there's only 3 bonds. One of them's a lone pair, and the shape is really what we view the shape as just the atoms bonding. The lone pair is there and influencing the shape itself. So the shape of NH3 would be pyramidal or trigonal pyramidal. So you should be familiar with all the shapes that we went over in class, and how VSEPR predicts those shapes, counting up electron domains, whether they're bonded domains or lone pair domains, and you can walk through this chart to give you some ideas of some of the molecules that we saw and the shapes that they take up on this page and on this page. Okay, so you can go through those on your own. Then we looked at bond polarity. Bond polarity is using the electronegativity of 2 atoms that are bonding together, and using the electronegativity to predict, is the bond going to be more covalent or ionic? One big takeaway in bonding is that we should view bonding as a continuum, as a scale, not as in black and white situation, as a binary. It has to be either ionic or covalent. Although we describe bonds as being either ionic or covalent, the truth is bonds are either more ionic or more covalent. Because at the end of the day, a chemical bond is just an electrostatic attraction of 2 atoms, and it's all about the degree to which the electrons are being shared. They're either being shared equally, which is the nonpolar covalent bond that's all the way at this end of the scale or the continuum. And as the elements, if we look at the different combinations here, as the difference in electronegativity between the 2 elements increases, the pair of electrons shared between them continues to move towards 1 atom. Eventually, the electronegativity becomes so great that the atoms are not sharing electrons anymore, and the bond is considered to be more ionic. We said that was around 2, but again, that was just an estimate based on observations that we see. So you should be familiar with classifying a bond as ionic covalent, and then polar covalent or nonpolar covalent based on the difference in electronegativity. Now, the bond polarity ultimately led to classifying molecules as being polar or nonpolar. Molecular polarity has to do with the shape of the molecule, and if a molecule has a positive or negative end associated with it. Something like water has 2 polar bonds. This oxygen-hydrogen bond is polar. This oxygen-hydrogen bond is polar. And because of the asymmetric shape of the water molecule, those 2 polar bonds, the way that the oxygen's pulling up the electrons from the hydrogen, if we add those forces, really, we're going to get an overall pull of electrons up in that direction, which makes this end of the molecule more negative and that end more positive, right? Partial negative and partial positive. So water would be considered a polar molecule because of that. Where in CO2, and these are double bonds, by the way, there is a polar bond. This bond is polar. The oxygen is pulling the electrons more towards itself. But this bond is identical and is also polar. And because the shape is symmetric, because it's linear, this bond dipole here cancels with this bond dipole over here, and there is no net pull of electrons to one side of the atom or the other. Therefore, there's no partial positive or negative end of the molecule, and therefore we consider this molecule to be nonpolar. So you can look at some examples here of some polar and nonpolar molecules. Again, it has to do with the bond polarity and the way that if there are dipoles present, are they arranged symmetrically in which they cancel each other out, or are they arranged asymmetrically in which we're going to get one end of the molecule to be more negative and one end to be more positive based on the distribution of electrons in the molecule. The final thing we looked at was intermolecular forces. And we looked at the difference between intra, which means within, and inter, which means between. An intramolecular force is just a bond. And we looked at ionic, covalent, and metallic bonding in this chapter. And here's a relative ranking of energy. It's really, really hard. You can see there's overlap. It's really hard to say, is an ionic bond stronger than a covalent bond or a metallic bond? Because bonding, it's not a physical, the energy involved is, well, energy, and it's not a physical, tangible thing. But we can see the energy involved in breaking ionic, covalent, or metallic bonds. There is some overlap, and each one is different for different reasons. Like ionic bonding is different because I have a bunch of positive ions and negative ions bonding together, where in a covalent bond I do have a specific number of atoms that are sharing electrons. But it all comes down to Coulomb's law, which we've seen time and time again. The distance between the two atoms as it gets smaller increases the attractive force between two atoms, and the charge, if there is one present, of either atom or either ion, as that increases, that also will increase the force of attraction between the two particles. Intermolecular forces are the forces that exist between molecules. So just by definition, a molecule is a particle which contains atoms that are covalently bonded together. So ionic and metallic substances do not have intermolecular forces. The only thing that's holding them together are their bonds. Covalent substances have covalent bonds that are holding the atom together, but then have intermolecular forces that are holding one molecule to another. And the three types were London dispersion, or we just call them dispersion forces, dipole-dipole, and hydrogen bonding. Dispersion forces were the weakest intermolecular forces. They exist in every single molecule, and it has to do with the random fluctuation of electrons from one side of a molecule to another. This is the most prominent force in nonpolar molecules because it's the only force of attraction they have to stick together. In a polar molecule, because they do have a partial positive and negative end, in a permanent partial positive and negative end, that's going to cause them to link up like magnets, and opposite ends will link up together, partial positive next to partial negative. That is a stronger, obviously, intermolecular force than just the random fluctuation of electrons that allows molecules to link up. That is a dipole-dipole force. So polar molecules, the dipole-dipole force is most prevalent in polar molecules. Polar molecules have dipole-dipole end dispersion, but dipole-dipole is most prominent, meaning it's the strongest there. And then hydrogen bonding is really, we said, a really bad misnomer because it's not a bond at all. It's an additional type of intermolecular force, and it's really just another type of dipole-dipole. It's a super, super strong type of dipole-dipole attraction that exists between polar molecules that specifically have hydrogen, but that hydrogen needs to be bonded to fluorine, oxygen, or nitrogen directly. That's the only case in which the molecule will have that strong hydrogen bonding as an intermolecular force. We said it has to do with how small fluorine, oxygen, and nitrogen are, and how electronegative the elements are as well. We looked briefly in this chapter at what we can use intermolecular forces for. We can use intermolecular forces for looking at phase of matter. The stronger the intermolecular force, the more likely it is to be a liquid or a solid. The weaker it is, more likely it is to be a gas. Of course, there's a range, so there's no absolute, like if it's dispersion, that it has to be a gas. But we can use them to try and explain some observable properties, knowing that as the intermolecular forces increase, the force of attraction between the molecules increases, which is going to do things like increase the melting point and the boiling point, make it less volatile, increase specific heat. and turn the substance from gas to liquid to solid. The last thing I gave you for chapter 5 is the summary chart that was right out of our notes. I like this chart because it really does summarize all of the information that we've looked at in one location. So I would highly suggest that you look over this to make sure you have a good general understanding of the chemical bonding chapter that we went over. This brings us to the end of bonding part 2. So you should be ready to take your throwback quiz for chapter 5.